Good evening, everybody. So today we will do electrolytic cells first in our second session of electrochemistry. So electrolytic cells are exact reverse of galvanic cells. Here electrical energy is used, current is used to make a non-spontaneous redox reaction occur. So in an electrolytic cell, current is used to make a non-spontaneous redox reaction occur. And also we can say electrolytic cell is a device which converts electrical energy to chemical energy. So this is how an electrolytic cell is going to be defined. So let's start by taking a few examples and to understand that whenever we are doing our electrolysis, what will be the products? What will be the product at cathode? What will be the product at anode? So first example I will take is of electrolysis of molten NaCl. So how we make a electrolytic cell? You will take a beaker and whatever is the electrolyte we will fill in this. In this example, our electrolyte is molten NaCl. So we will fill molten NaCl in this beaker and we will dip 2 plates of platinum. These are 2 electrodes and connect it with a battery. Connect it with a power supply. Okay. So this is typical design of an electrolytic cell. 2 plates dipped in electrolyte connected with a power supply. Now, the moment we switch on this battery, this platinum plate is connected to negative terminal of battery. So this will be our negative terminal or negative plate and this will be positive. And electrolyte is molten NaCl. Means electrolyte will contain Na plus ions and Cl minus ions. The moment these plates are connected with battery and they acquire a charge, an electric field will be set up between these plates. Now these both plates are acting as a parallel plate capacitor. So electric field will be set up between these plates. This plate is negatively charged, so sodium ions will start to migrate here. And this plate is positively charged, so chlorine ions will start to migrate here. Okay. Now, once sodium ions reaches this plate, to flow complete current in circuit, sodium ions will have to do a charge exchange at this plate, or sodium ions will have to undergo this reaction. Na plus a electron, they will take electron from the plate because this plate is negatively charged, means this plate has excess of electron. So sodium ions will take electron from this plate and get converted to sodium. Now E naught of this reaction is minus 2.7. A negative E naught is indicating that this reaction is non-spontaneous. This does not want to occur. But still then why it will occur? This will occur due to battery. Battery is trying to flow current in this way. Correct? So this reaction will only occur if the spontaneity of battery, the voltage of battery exceeds this value. This is what we had written in our first line. Current is used to make a non-spontaneous reaction happen. So here we are using a battery whose voltage or spontaneity is greater than non-spontaneity. And similarly on the other side, chlorine ions will reach on this plate. This plate is positively charged. So it has deficiency of electron. To make the circuit complete, chlorine ions will have to do a charge exchange here, or they have to undergo this reaction. Cl minus goes to half Cl2 plus I electron. And E naught of this reaction is minus 1.36. This is also negative, again indicating this is also non-spontaneous. Correct? So if this circuit has to work, this electrolytic cell has to work, the EMF of the battery should be greater than this total value. Now, this is a typical working design of an electrolytic cell. At this electrode, we can see reduction of sodium ions is taking place. Reduction is taking place. So this will be our cathode. And on the other hand, here oxidation of chlorine ions is taking place. So this will be. So these will be the respective reactions at cathode and anode. And you might be asked, several problems are like that also, that they will give you a electrolysis and ask you what are the products. So now here, suppose if you are asked this same question for electrolysis of molten NaCl, then your answer would be that at anode, chlorine gas will be liberated. And at cathode, solid sodium will be deposited over the cathode plate. Okay. So this is electrolysis of molten NaCl. Let's move to our next example. Next example I will take is of electrolysis of aqueous cells. So now, in our electrolytic cell, we will take NaCl dissolved in water and 2 platinum plates. Connected with the. So this is cathode. And this is anode. Now, in case of aqueous salt solution, see, in case of molten salt solution, there was only one cation and one anion. Okay. Cation migrated towards cathode, anion migrated towards anode, and their respective oxidation and reduction occurred at respective electrons. But in cases of aqueous salt solution, now here what change will occur with our previous discussion, that here salt will have its cation and anion, that is one thing. Apart from that, since water is present, water will also produce H plus ions and OH minus ions. And water itself is there. So there are several things which now can be reduced or oxidized at various electrodes. So in such case, when there are more than one possible reactions at electrode, then we apply preferential discharge theory. And preferential discharge theory says that at any electrode, that reaction will occur which is most spontaneous. Okay. So like for example of cathode in this case, I can have 3 possible reactions. What are those 3 possible reactions? I can have reduction of sodium ion, whose E naught value just now we saw minus 2.71. We can have reduction of H plus ions, whose E naught value we discussed in last class will be 0. Or we can have reduction of water itself. What value is minus 0.827. So now, out of these 3 reactions, we have to decide which reaction will occur at cathode. And here is where we will apply preferential discharge theory. And preferential discharge theory says that the reaction which is most spontaneous, that is going to occur. Now, out of these 3 reactions, I will first rule out reaction number. Why I will rule out reaction number 2? Because as you know, NaCl is a salt of strong acid and strong base. And pH of such a salt solution is 7. So pH of aqueous NaCl solution is 7. pH 7 means concentration of H plus ions is 10 raised to minus 7. And in electrolysis, if concentration of any ion is such low, in order, see here we are seeing 10 raised to minus 7, then we say that the availability of this ion near the plate is negligible. So we say this ion is not even available substantially around the plate. So we never consider such ion whose molarity is so low. So low availability of, and due to which we rule out this reaction. So now out of the remaining two, that is first and third, we can see clearly E naught of this is much greater than this, and hence we will say this will get a preference over first reaction. So now you can see the difference. When we were doing electrolysis of molten NaCl, then at cathode the product was solid sodium. But if we are doing electrolysis of aqueous NaCl, then at cathode the product is hydrogen gas and OH minus ions. Okay. Now similarly, let's move to the anode side. What is happening at anode? So anode, again, we can have possible oxidation of fluorine. Whose E naught value we discussed was minus 1.36 volts. OH minus I will not again consider because OH minus also has a molarity of 10 raised to minus 7, correct? And such low molarities we will never consider. Clear? And next is, yes, oxidation of water. So we can have possible oxidation of water. H2O goes to half O2 plus 2H plus 2 electron. And E naught of this reaction is minus 1.23. Now, here a very important point comes, a very special feature occurs. Now, if I see the E naught value, what I will say, E naught value of second reaction is greater than first. So according to this concept, water should be oxidized at anode and oxygen gas should be liberated. But when we practically do this electrolysis, we find that at anode, chlorine gas is liberated. First reaction is happening. Now this reason, the reason here is attributed to a term which we call as over. See, what is over voltage? Over voltage is the slight extra voltage we require for liberation of species. तो यहाँ जो ये क्लोरीन गैस या ऑक्सीजन गैस they have to be liberated. They require some slightly higher voltage than their recorded values. Okay. So this slight extra voltage is known as over voltage. And the E naught value of chlorine liberation and oxygen liberation are very close. So after taking over voltage into account, this becomes the more spontaneous reaction. And therefore, chlorine gas is liberated here, not oxygen. Okay. So for this pair only such a reversal occurs because their E naught values are very, very close. Okay. So this is electrolysis of aqueous NaCl. The products here being at cathode, hydrogen gas and hydroxyl ion, At anode, chlorine gas will be liberated. Okay. Now in the same electrolysis, we can make one further change. In this same electrolysis of aqueous NaCl, if I make the cathode of mercury, rather than platinum, we take it of liquid mercury, then what changes are going to? Now what difference will occur here? Anode side, so we have not made any change, so no difference. Cathode side, the two reactions which we were discussing. Out of these two, see, mercury is liquid, and over liquid liberation of gases is extremely difficult. Okay, over liquid, we cannot have liberation of gases. They have a very high overload. So here, this reaction will occur. And this will not occur due to extremely high over. Liberation of gases over liquid mercury is almost very improbable. They have a very high overload. Correct? So if we take a liquid mercury cathode, then at cathode reduction of Na plus ions will occur and not of. So these three electrolysis regarding NaCl, I hope is clear to everybody. Molten NaCl, anode chlorine gas, cathode solid sodium. Aqueous NaCl, anode chlorine gas, but here the important point came of over voltage. Cathode, hydrogen and hydroxide. Using mercury cathode, at cathode, sodium mercury amalgam will be formed. Sodium will also not be formed in solid state here. There will be no deposition of solid over liquid mercury. So sodium mercury amalgam will be. So these are few cases I discussed in electrolysis of NaCl. Now let's change the solid. And the next example let's take is electrolysis of aqueous copper sulfate. Okay. Now here, again let's make a electrolytic cell. electrolyte is aqueous copper sulfate. And we put 2 platinum cubes and connect the battery. Now, at cathode side, let's check the possibility. What is going to occur? So at cathode side, the possible reactions that can occur. One is reduction of copper. CO2 plus 2 electron goes to CO. T naught of this plus 0.34. Another reduction of water. T naught minus 0.8277. Correct? Out of these, we can clearly see that E naught of copper is much bigger. So here what will happen? Copper ions will get reduced and copper will be deposited over cathode. Okay. So this is an electrolysis of aqueous copper sulfate. Let's move to anode side. Let's move to anode side. Now anode side, which ions have came? First of all, one ion is sulfate. Now in sulfate, you can see that sulfur atom is already in its highest oxidation state. Oxidation state of sulfur in sulfate is +6, which is the highest oxidation state of sulfur. So sulfur ion obviously cannot be, sulfur in sulfate ion could not be oxidized any further. Okay. Yes, the oxygen might get oxidized. So one possible reaction that can occur is 2-sulfate goes to S2O8 2 minus plus 2 electron. T naught is around -2 volts. And then obviously we have oxidation of water. T naught is -1.23. So here again I can see that oxidation of water is much more spontaneous. So in electrolysis of aqueous copper sulfate, at cathode copper will be deposited, at anode oxygen gas will be liberated and H plus ions will be present. So this is electrolysis of aqueous copper sulfate. And the next example I will take. इलेक्ट्रोलिसिस ऑफ एक्वस कॉपर सल्फेट ही है अभी, पर थोड़ा सा चेंज किया है। क्या चेंज किया है? एनोड को कॉपर का किया है, प्लैटिनम का नहीं। Anode ko we have made a copper plate. So now what will be our situation? Aqueous copper sulfate. Cathode, let's say, still I have kept platinum. Anode I have made a copper. So cathode side, so there will be no change. No need to discuss that again. Anode side. Now, one reaction was oxidation of sulfate, E0 minus 2 volt. One was oxidation of water. E0 minus 1.23 volt. But copper is an active metal. It is not an inert metal like platinum. So what another possible reaction now that can occur, that copper from the plate starts to get oxidized. And this E0 is minus 0.34. So now out of these three values, this is the highest value. And therefore, if I do electrolysis of aqueous copper sulfate, then what will happen? Then at anode, the plate will dissolve as copper ion in the solution. Okay. So these are few examples which we have discussed. And using these examples, now let's generalize what happens in electrolysis. So, सबसे पहले, if I am doing electrolysis of a molten salt की electrolysis में क्या होगा? Molten salt की electrolysis में कोई choice नहीं है चाचा हमारे पास. So in electrolysis of molten salts using inert electrodes, that is platinum, using inert electrodes, you have no choice. Whatever is the cation of salt, cation is reduced at cathode and anion is oxidized at anode. So here you have no choice. अगर inert electrode है तो जो भी cation है उसी that has to be reduced at cathode. And whatever is the anion that has to be oxidized at anode. Which was our first example. Here, we didn't have any choice. सोडियम कैटायन था, उसको हमने वहां पे करा लिया. Sodium cation we got reduced at cathode. Chlorine anion we got oxidized at anode. In case of aqueous salt solution, yes, that is going to be the tricky part. So in case of aqueous salt solutions, electrolysis of aqueous salt solution. Here, How do we decide that which reaction is going to occur at cathode and which reaction is going to occur at anode? Where? Let me start the discussion for cathode. And first situation I take. If I have made cathode of a platinum, which is commonly used, then all cations I will divide in two categories. One are cations of highly active metals, like Na+, and other are cations of lesser active metals, like Cu2+. The first category I am making cations of highly active metals. Which will contain definitely alkali metals, alkaline earth metals, aluminium, etc. Or all those cations whose SRP value is less than -8277. In such a case, what will happen? In such a case, water, yeah, or H plus if it is acidified, water will be reduced at cathode by this reaction. So in such cases, product at cathode will be hydrogen gas and hydroxyl ion. Whenever you are doing electrolysis of a salt which contains cation of highly active metals. But in contrast, if you have a cation of lesser active metal, mostly P and D block metals, in such a case, what will happen? In such a case, cation will be reduced at cathode by this reaction. Whatever is the metal, its cation will be reduced and that cation will be deposited at cathode. This is discussion if we are doing using a platinum cathode. If we are using a mercury cathode, over mercury, hydrogen liberation has a extremely high over voltage. So over mercury, whichever cation it is, cations of all metals, what will happen? Always that metal cation will get reduced and respective metal amalgam will be formed. Okay. With mercury cathode, reduction of water never occurs. Always reduction of cation occurs. Okay. So this is how you can decide what is going to be the product at cathode. Now, similarly, if I come to anode side, for discussion of anode side, take if anode is of platinum, that is an inert metal. In this case, if our anion is Br minus or I minus, bromide or iodide, their E naught value is much greater than E naught of water oxidation. So in these, if these are anions, what will happen? Anion will be oxidized. And respective halogen will be released. Respective halogen will be liberated. So basically, if Br minus is there, then Br2 will be liberated. If I minus is there, then I2 will be liberated. If the anion is Cl minus, then also Cl minus is oxidized, will be oxidized, and Cl2 gas will be liberated. But here, this is happening due to overload, because E naught value was greater for water. Okay, and therefore, if I take a very dilute Cl minus solution, in this case, water is oxidized and O2 gas is liberated by this reaction. 2H2O goes to O2 plus 4H plus 4. Okay, because if we make the chlorine solution very dilute, due to Nernst equation, CMF will be dropped, and then the difference in E naughts of chlorine and water will be larger, which will not be compensated by overload. And if our anion is F minus, in F minus, the E naught value of F minus is much lower than water. So for F minus, over voltage cannot play any role, and therefore water is oxidized and O2 is liberated. Then next cases we can discuss are oxo ions with central atom in highest oxidation state. Like for example, phosphate, sulfate, carbonate, etc. In such case also, water is oxidized and oxygen is liberated. And another situation at anode we can discuss. If we make anode of a active metal, like in last example, we made anode of copper. So if we make anode of a active metal, then what happens? Then the metal itself gets dissolved. So then what will happen? The metal of the plate will itself get oxidized and dissolve in the solution. Then anion is not oxidized. So this is how we will decide the product at cathode and anode. If we are doing electrolysis of any aqueous salt solution. Okay. Now, by these we can decide these all concepts that what is going to be the product at cathode and anode. That will be one part of our electrolysis problem. The next point will come, how to calculate how much product is formed. Whatever is being formed, copper or chlorine gas, whatever is being formed at any electrode, how much it is formed. So for that we use Faraday's law. And what are Faraday's laws? First law states that Faraday's first law, what does it say? That the weight of substance deposited or liberated at an electrode is directly proportional to the charge passed through electrode. Basically, first law is saying, suppose some substance X is being liberated at any electrode, then the weight of X liberated will be proportional to the charge passed through by it. And Faraday's second law of electrolysis states that if equal charge is passed through several electrodes, then the ratio of weights of substances produced at electrode is equal to ratio of the equivalent weight of substances. So basically, अगर दो अलग-अलग, so at two different electrodes, let's say at first electrode a substance X is being liberated, and at other electrode some substance Y is being liberated, and we are passing same charge through both electrodes. Then according to this law, weight of X by weight of Y will be equivalent weight of X by equivalent of. So by these two laws of Faraday, we will calculate weight of substances produced at various electrodes. Okay. Both of these laws can be combined in one simple equation. And what will be that equation? That equation we can write like this. That let's say some substance X is being liberated at any electrode. Then weight of X upon equivalent weight of X. This is number of equivalents of that substance X. Correct? And this will also be equal to the moles of electron flowing through the electrode in electrolysis, which you can give by IT by F, where I is the current flowing through the electrode, T is time in seconds for which it is flowing, and F we had discussed in last session also. F is 1 Faraday, which is equal to 96500. So this result we will use. And by this we can find in any problem what is the weight of substance liberated at any unit. Okay. Let's take a quick 1 or 2 PYQs on electrolysis and try to understand how we will apply Faraday's law. Now, I like this one PYQ we can see. Integer type. The amount of charge in Faraday required to obtain 1 mole iron from Fe3O4. Correct? So they are asking you amount of charge in Faraday. Amount of charge in Faraday, it means they are asking you this thing. How many moles of electrons? Because 1 Faraday is 1 mole of electron. Okay. Let's apply this relation. So I want to find moles of electron. Moles of electron will be weight of X. And X here is, what is X here? Iron. Weight of iron upon equivalent weight of iron. How much iron I want? 1 mole. So weight of 1 mole iron is, iron atomic weight we know is 56. Equivalent weight of iron. Iron we are making from Fe3O4. Here the oxidation state of iron in Fe is 0. And here it is 8/3. So what is the change for this? What will be N factor for this? Difference of these two, that is 8/3. So equivalent weight of iron will become atomic weight divided by 8/3. So our answer becomes 8/3. How many moles of electrons are needed? 8/3. Okay. Let's take one or two more examples. Then we will move to conductance. Next example, let's take like this. You are given potassium chlorate, potassium chlorate is prepared by electrolysis of KCl in basic media by following reaction. 6OH minus plus Cl minus goes to ClO3 minus plus 3H2O plus 6 electron. Okay. So this is the reaction given to you. You are if 60% current is used in electrolysis, then find the time required to produce, then find the time required to produce 10 grams KClO3 using 2 ampere current. Using 2 ampere current. Okay, direct application. W weight of KClO3 upon equivalent weight of KClO3 will be I into T by F. How much weight KClO3 we want to produce? 10 grams. Equivalent weight will be molecular weight by N factor. And N factor here directly we can see is 6. With 1 ClO3 minus there are 6 electrons. So N factor we can clearly see is 6. And molar mass of KClO3 we can take 122.5 by N factor is 6. Current is 2 ampere but only 60% of that is used. Time we have to find F965. By this we will get time in seconds. In problem time was asked in hours. Then you can convert that seconds into hours. Whatever this answer you will get, this will be in seconds. Then you can convert it appropriately to hours. Okay. So is the problem clear? How you see N factor, number of electrons involved. So in electrolysis, this is the type of problems you are going to get. Let's move to the third part of chapter, that is conductance. So, there are two types of conductors of electricity. One are metallic conductors and other are electrolytic conductors. Metallic versus electrolytic. A quick conceptual understanding that what are differences between metallic conductors and electrolytic conductors. In metallic conductors, charge carriers are free electrons. So free electron move from one place to other inside a metal, and that is the reason for their conduction. On the other hand, in electrolytic conductors, charge carriers are ions. So the substance which is carrying charge is different. There is the big difference. In metallic conductors, the charge carriers are only negative charges. Only electrons conduct electricity, flow electricity. But in electrolytic conductors, the charge carriers are both cations as well as anions. So in electrolytic conductors, charge is carried on by both positive and negative charge. But in electrolytic conductors, charge is only carried by negative charge. Next difference. So metallic conductors have a property known as resistance, which everybody must have studied. Now, why there is resistance in metallic conductors? Resistance in metallic conductors is due to the collisions between metallic lattice and that free electron which is moving to conduct electricity. And similarly, electrolytic conductors also have resistance. So in electrolytic conductors, the resistance is due to first cause is interionic attraction. Because here both cations and anions will be moving and they are oppositely charged, they will attract each other, they will cause hindrance in movement of each other, and due to this interionic attraction, there is resistance. Another cause of resistance is hydration. Many water molecules or solvent molecules will stick around the moving ions, making them bulkier and difficult to move. And obviously, there will be viscosity, friction for moving between the liquid layers. So these are the causes of resistance in electrolytic conductors. And the third difference which we can write in metallic conductors, as temperature is increased, their resistance increases and conductance decreases. Because as temperature is increased, the lattice will begin to vibrate and there will be more collision and that will cause resistance to increase. But in contrast, in electrolytic conductors, as temperature is increased, conductance increases and resistance decreases. So temperature dependence is exactly opposite. In metallic conductors, if you increase the temperature, resistance will increase. In electrolytic conductors, as you increase the temperature, conductance will increase. Now, let's come to electrolytic conductors. So the numerical definition is same as of metallic conductor. In metallic conductors, if you remember, we define resistance as rho L by A rho L by A, where rho was resistivity, L was length of wire, and A was area of cross section of wire. This is the same definition we will use for electrolytic conductors also. So if I take any electrolytic cell, and these are the plates. So here, L we define this. L we define as distance between plates. And A is area of this L by A together is called as cell constant. So same thing we define resistance of electrolytic cell in the same way. Rho is resistivity or specific resistance. L is distance between plate and A is area of the plate. So here we define for electrolytic conductors kappa as 1 by rho, and 1 by rho you can see from the above equation will become 1 by R into L by A. So this kappa is known as specific conductance or conductivity, and its units will be ohm inverse meter inverse. If you take L and A both in meter and meter square respectively, but generally length and area we will use units of centimeter and centimeter square. So then the non-SI unit will be ohm inverse centimeter. Ohm inverse is also written as mho or Siemens. All are one and same thing. Unit of conductance, ohm inverse or mho or Siemens. Okay. So this is kappa, specific conductance. 1 by R is conductance. Now, for metallic conductors, only defining rho or kappa was sufficient. Because if I take several pieces of copper wire, if I just tell kappa of that or rho, our whole problem is solved. Because the number of free electrons in copper per mole will remain same. That is the inherent property. So, in metallic conductors, the number of charge carriers is fixed for any particular metal. We cannot change that. We cannot change the number of free electrons in 1 mole copper. Okay. But in electrolytic conductors, the charge carriers are ions. And those ions are coming from the salt which we have dissolved in water. And the amount of salt which we are dissolving in water is in our control. So in electrolytic solutions, electrolytic conductors, only defining kappa is not sufficient. I cannot give you just like this kappa of NaCl because kappa of different molarities of NaCl will be different. I can make a 0.1 molar solution of NaCl and I can make a 0.2 molar solution of NaCl. Now 0.1 molar solution NaCl and 0.2 molar solution NaCl will have different number of ions. And if they have different number of ions, then their kappa is going to be different. So therefore, for electrolytic conductors, we define one more term, which is called as molar conductance, and it is denoted by lambda. So how is molar conductance defined? This is how we define molar conductance. That molar conductance is conductance of that much volume of solution, of that much solution, which contains 1 mole electrolyte between plates which are unit distance apart, and the plates are large enough to contain entire electrolyte between. So this is how we are defining molar conductance. Okay. So how are molar conductance and specific conductance related? Let's see that. So the relation between molar conductance and specific conductance we can give like this. Here units are going to play an important role. So for specific conductance, I had 2 units. Either I can have a specific conductance in per ohm per meter, or I can have specific conductance in per ohm per centimeter. So if I'm using specific conductance in per ohm per meter, then the relation here is lambda n so units will be ohm inverse meter square mole inverse is equal to kappa, whose units will be ohm inverse meter inverse into 1 upon 1000 into molarity of solution. So the relations will be like this. Lambda f ohm inverse meter square mole inverse kappa in unit of ohm inverse meter inverse into 1 upon 1000 molarity, and units will be meter cube per minute. But if you are going in units of centimeter, then the same result will be lambda m will be ohm inverse centimeter square mole inverse is kappa, which will be in ohm inverse centimeter inverse multiplied by 1000 upon molarity centimeter cube. So this is how kappa and lambda m will be related. Here, while applying the relation, you have to be very careful regarding units. That whether you are taking units of meter or centimeter, accordingly 1000 will either come in numerator or in denominator. Okay. And just like molar conductance, we also define equivalent conductance. How we define equivalent conductance? lambda E. Similar type of definition. Similar definition, thus the change occurred here is instead of 1 mole, now it is 1 equivalent. How is equivalent conductance defined? It is conductance of that much solution which contains one equivalent of electrolyte between plates which are unit distance apart and large enough to contain entire electrolyte between. Okay. So this is how we are defining equivalent conductance. And very similarly, we can write a relation of them with kappa, like we had written for molar conductance. We can also write it for equivalent conductance. Again, we have to see for what we have to take care. We have to take care of units, whether they are of centimeter or of meter. Okay. So same relations now will be lambda E in ohm inverse meter square equivalent inverse is kappa in per ohm per meter into 1 by 1000 normality meter cube per equivalent, or lambda E in ohm inverse centimeter square equivalent inverse is equal to kappa in per ohm per centimeter into 1000 by normality centimeter cube per equivalent. And lambda E and lambda M are related like this. Lambda M is lambda E multiplied by M factor. Now, the important part of this section, let's come, that we have to understand how will these three variables, these three terms, kappa, lambda E and lambda M, will change if we dilute the solution. If we dilute the electrolytic solution, how will they change? Variation with dilution. See what will occur due to dilution. When you dilute a solution, the molarity of the solute will go down. Molarity of solute will go down. That means the number of charge carriers, the number of ions that were carrying charge per unit volume, that has decreased. Number of charge carriers per unit volume have decreased. Correct? But since the solution is now more dilute, the distance between ions has increased, interionic distances have increased, and therefore interionic attractions have reduced. And if interionic attraction reduces, each ion will now be in a better position to conduct electricity. So, on diluting a solution, two factors are operating. One, the number of charge carriers is getting reduced per unit volume. And the second, each individual charge carrier is now in a position to conduct electricity better. Okay? So therefore, as we dilute a solution, means as we decrease molarity of a solution, what will happen? Kappa, which was specific conductance, means conductance of a unit volume solution. For that, what will happen? For that, the dominant factor is the first factor. That is, number of charge carriers have decreased. And therefore, the value of kappa will decrease. So as you decrease molarity, the value of specific conductance will decrease. But on the other hand, molar conductance was conductance of 1 mole electrolyte. Now, whether you dilute the solution or what, the number of ions there you have kept fixed. You want to find conductance through 1 mole electrolyte. Okay. So number is fixed and each ion is in a situation to conduct electricity better. So lambda M and lambda E are going to increase. So this is an important point, has been asked in one or other way several times in exams. So this we should know. As molarity is decreased of a solution, its specific conductance will decrease, but its molar conductance and its equivalent conductance will increase. Now, the variation of molar conductance with molarity was studied in detail experimentally by scientists like Debye and Akal. And what they found was, for several electrolytes at their different molarities, they measured their lambda value. And when they tried to plot it on a graph, they made a graph of molar conductance versus rho C. And what they found was for strong electrolytes, this graph is a straight line. So for a strong electrolyte, lambda m versus root C graph was a straight line. But for weak electrolyte was a curve, not any specific shape for weak. So this is what they found for different electrolytes. Now, by this graph, we can see as C is decreasing, lambda m is increasing, both for strong as well as weak electrolyte. So, for any electrolyte, if we are asked, when will be the maximum value of lambda m? What will be our inherent answer? Immediately, what answer we will give? We want to find at what molarity, at what situation, lambda m value for an electrolyte is maximum. And by the graph, it is clear that the maximum value of lambda m will occur when C approaches 0. So, what we are trying to say, the value of lambda m will be maximum as C tends to 0. So as molarity of that electrolyte tends to 0, the value of lambda m will be maximizing. And the moment we realize that, another thing we should understand, polarity tends to 0 means we have not put electrolyte or a very small amount. So practically it is not possible to measure this value. Because if we are not putting any electrolyte, how we will measure lambda m of that electrolyte? Correct? So experimentally this value cannot be measured. So what we call this value of lambda m will be maximum at T tends to 0, and this maximum value is called limiting molar conductance or 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 the other name we give it is molar conductance at infinite dilution. And the symbols which we will use to denote it is lambda m naught or lambda m infinity. Okay. Now, next point also clear to us. Can't be measured. Experiment. So now how to calculate this value, because this is definitely going to be an important value for us. So what was thought by various scientists here, if you see, for strong electrolytes, the graph of lambda m versus root C was a straight line. So what they assume that strong electrolytes will follow the same pattern throughout the graph, yeah, for the overall range of C. So what they did was they extrapolated this graph. There were no experimental data here when C was tending zero. There were data experimental measurements for some finite C. By those measurements, they made this line and then they extrapolated, they produced it backward. And wherever it intercepted y-axis, that was called the lambda m infinity value for strong electrolyte. So strong electrolyte, this method was thought. Yeah, this method is used to calculate their limited molar conductance. But for weak electrolytes, we can't even do this. You cannot extrapolate this type of curve. So, what further we can see? For strong electrolytes, so for strong electrolytes, lambda infinity value can be calculated by extrapolating their lambda m versus root C graph. Correct? For strong electrolyte, we can write the equation of this straight line. How we can write? For strong electrolyte, their lambda m I can write as lambda y is equal to mx plus c. Cy intercept is lambda m infinity and slope is negative. Some constant b times root c. So for strong electrolytes, we can write an equation like this. That lambda m is equal to lambda m infinity minus b root c. Okay? But for weak electrolyte, still we didn't have no solution. So here, now a law is given. Polar outlet law. What this law tells us, So what is Polar-Auschwitz law stating? Polar-Auschwitz law is stating that at infinite dilution for any electrolyte, its molar conductance can be represented as sum of molar conductance of its ions. Means we have any electrolyte like AB. So lambda m infinity of AB, I can write as molar conductance of A plus molar conductance of B. But this we can only do at infinite dilution. Okay. Now, how we will use this law to find lambda m infinity of weak electrolytes? See, let's take a weak electrolyte, for example. Let's take acetic acid. So we are interested in finding lambda m infinity of acetic acid. We know acetic acid is a weak acid. Okay. So now, what we can say by Polar-Auschwitz law, I can say lambda m infinity of acetic acid will be lambda of H plus and lambda of acetate ion. Correct? Now, I will try to think of some other ion with which these ions make a strong electron. Like H plus ion. I know a strong electrolyte of H plus ion is HCl. So what I do, I write this as lambda of H plus lambda of Cl minus lambda of Cl. I add and subtract lambda of Cl. Similarly, next I see acetate ion and I try to find another ion which makes a strong electrolyte with acetate ion. And ion comes to our mind is sodium. Sodium acetate is a strong electrolyte. So I add and subtract conductance of sodium ion. Lambda of Na plus minus lambda of Na. And obviously this acetate ion. Now, if I see these first two together by Polar-Auschwitz law, I can write lambda m infinity of HCl. Similarly, the other two I can write lambda m infinity of sodium acetate, and the last two I can write lambda m infinity of Na. Now NaCl, HCl and sodium acetate, all these three are strong electrolytes and their lambda m infinity values I can easily get from their respective lambda m versus root C graph. So these three values I can get by their graph, and therefore by this combination I will get lambda m infinity of acetic acid. Correct? So this is how we are going to use Polar-Auschwitz. And here also one more thing we can write. One more expression we can use. For a weak electrolyte. Or a weak electrolyte. Let's say at when its concentration is some C, and at that concentration, molar conductance is lambda. So alpha at this concentration, degree of dissociation, is given as lambda m by lambda m infinity. Because at infinite dilution, you know, alpha is going to be 1. One more thing, what we should know in conductance, that if in a solution there are more than one electrolyte, there are several electrolytes, then you can add the conductance of those solutions. So total conductance, G total, is given by summation of Gi. So if you have more than one electrolyte in same solution, you will add their conductance. And generally, conductance of water is very less. But suppose the problem is giving you its numerical value, then you can include that also. Total conductance of any solution is going to be summation of Gi plus G water. G, all of you remember G is 1 by R or kappa into A by M. Okay. So in a solution of several electrolytes, you will add their G values. And if you substitute the expression of G, if all electrolytes are in same cell, obviously, then A by L is going to be same for all of them. So this result you can also write as total kappa is equal to summation kappa I plus kappa of 1. So in a solution of several electrolytes, you will add their kappa values, not their lambda values. Okay. Okay. So let's take one or two PYQs of conductance part also. Like this Polar-House's law problem came, you are given the limiting molar conductance for NaI, NaNO3 and AgNO3 are 12.7, 12.0 and 13.3 Siemens Siemens meter square mole inverse. Find lambda m infinity of AGM. Okay. So simpler result now you can use. AGI is a weak electrolyte. And you are given molar lambda m infinity value of 3 strong electrolytes. Let's apply Polar-Auschwitz law. So lambda m infinity of AGI. I will write lambda of AG plus lambda of I minus. Now by the data given, I can see I can write this as lambda of Ag plus lambda of nitrate plus lambda of Na plus lambda of I minus lambda of Na plus lambda of nitrate. So this is nothing but lambda m infinity of AgNO3 plus lambda m infinity of NaI minus lambda m infinity of Na. Values given are AgNO3 13.3, NaI 12.7, NaNO3 12. Answer is 4. Another problem, let's say. We are given resistance of conductivity cell. Containing 0.01 molar KCl at 298 Kelvin is 0.152 into 10 raised to minus 3 Siemens meter inverse. Sorry, centimeter inverse. Cell constant is asked. The cell constant is dash into 10 raised to minus 3 centimeter inverse. So you have to find this value. Let's say. So direct expression of kappa. Kappa was sorry. I just missed out one line. Resistance at 298 Kelvin is 1750. This was resistance given. And conductive, this is, and kappa A. Yes. So kappa ka relation 1 by R L by A. Cell constant is L by A, which you can see is kappa into R. Kappa given to us is 0.152 into 10 raised to minus 3 and R 1750. So that is one. 10 raised to minus 3 की terms में represent करना था. So just you have to multiply 0.152 with 1750. Okay, so this completes the second part of the chapter, that is conductance and electrolytic cells. Goodbye, everybody.